No. So this is the 15th week of the semester. So I guess technically this puts us at lecture 43, even though we clearly haven't had that many because of all the craziness and whatnot. So a couple things I just want to state before we get going. First and foremost, I am trying to keep up with emails. I'm getting a ton of them. I know I owe some of you some help. I just want to remind you that, feel free to email me, and if I don't respond, and then first day, please email me again. Right now, I'm getting, it's Tuesday, and most of the emails I'm getting to update on are from like Thursday and Friday of last week. So I'm not telling you that to discourage you from contacting me. I'm telling you that as my students, that if there is a question you don't know how to answer, do not hesitate to email me about it every day, so that I see it. Going through emails is insane right now. That said, the other important thing would be that next week is our technical final week. And what I'll be doing is I'll be posting the final. And I'm going to put all the details to this on Canvas. But just to give you an idea, because I know some of you are interested in this, final will be posted Wednesday of next week. So what does that make it? So the 1st is what? May 1st is Friday. Is that correct? Yeah, so that would be what? The 6th? And it'll be due the following week. So if you have any particular questions about your grades, or you have any particular questions about anything, just don't hesitate to ask. I'd be happy to set up a Zoom appointment. We can talk in person if you'd like. So please feel free to explode my email. And if you want to come at it from multiple angles, you can send a Canvas notification too, because when you use Canvas, it does two things. It emails me, but it also alerts my Canvas. So it's more likely that I won't miss it. Any questions at all about that, the generality stuff? Or I guess the more general things, finals, grades. Oh, another thing, a lot of you are concerned about, like, how you haven't updated my grades in Canvas and stuff. Hey, listen, I'm trying to. It's just, if I had a list of things that are important and that I thought were important for you, me updating your grades in Canvas is like the least of that, because, Canvas is not the official grade book. And so if I put things in the Canvas, that means I'm doing things more than once. I'm doing them in my grade book, and then I have to go look them up and put them in the Canvas. Now, that being said, I'm going to do my best over the next couple days to do it. It's just, it can't be one of my top priorities, because it's not. So if you are super concerned about where your grade is right now, send me an email and say, hey, can you give me a breakdown of where I'm at? That's much easier for me to do, and it's much more efficient for me to do it that way. So I don't know if that makes sense, but I'm hoping that it makes a little bit of sense. Does anybody have a question about any of that right now? My Math Lab or homeworks or exam, whatever? Going once, going twice? Okay. So I did want to do one example from homework. What is this one? Homework 10. A few people had asked about. And it's also still relevant to what we've been doing on the more other homework. So I think before we get into the most recent, we should look at this. Does anybody have a question about a homework 10 or anything before homework 10? I know, Katie, you had something with homework 6, I think. I just haven't had a chance to do it yet. I'm really sorry. I'm trying to get to it. Does anybody have anything? All right. So Cool. Then let's do this, and then we'll answer any other questions. I want to talk about these homeworks. So let's do number 4 on homework 10. So this problem asks us for a third degree or a third order Taylor polynomial centered at a point that is not 0. So one of the things that I am aware of, and those of you who've actually attempted the homework are aware of, is most of the stuff we've done has been centered at 0. These Taylor series, these Taylor polynomials, these power series, almost everything we've done has been centered at 0. And usually the reason for that is because when we're trying to learn it, the computations are easier. But that doesn't mean we shouldn't try to determine these things when we're not centered at 0. So problem 4 is an example of this where we don't want to use 0. So let's do that. So here's what we need to do. If we want the third order Taylor polynomial, we need to compute 3 derivatives for a specific function. So what is f of x? F of x is the 4th root of x. So I'm going to write it as x to the 1/4. And that means that the first derivative is 1/4 times x. Now what is 1/4 minus 1? That becomes negative 3/4. And so the second derivative becomes negative 3/16 x to the negative 7/4. And then last but not least, let's compute the third derivative, which becomes 21 over 64 x, and then I subtract 1 and I get negative 11/4. So before we go any further, does anybody have a question about this computation? Feel free to type it, feel free to say it, feel free to spray it. I don't care. Scream and yell. Notice my kids ain't here right now, so there's not chaos. It's calm.
Why? How'd you manage that?
They're out riding scooters. You know, it's crazy. I will say this. I mean, I have no idea how your other classes are going. I really don't. But I know, like, for me, the way I plan on grading your final and how as I already said with your grades, I am not being as strict as maybe I know I'm not being as strict as I would have been or in a normal semester, I should say. Because it's crazy how difficult it is for me to do things here at home. I couldn't imagine what sort of you guys are like. For some of you, you know, I have a house with multiple rooms, and even with Amy and the 2 kids, it's really hard to get peace and quiet. It's really hard to, like, I don't know how I would, you know, working is just completely more difficult now. And then I was thinking, like, what if we lived in an apartment, or who knows? Like, I have no idea what kind of scenarios some of everybody, or what you guys are dealing with. I mean, you might be living with roommates or parents, and you might not even have an hour a day where you get peace and quiet. So I have no idea how hard it is for you guys to learn in this particular environment. So I'm trying to understand and work out, or be understanding of all that. So hopefully you guys will give it your best, and we'll go from there. That's all we can really ask. All right, so if I want to compute a Taylor polynomial, this is what I have to do. I have to compute the derivatives. I mean, that's just, the problem says give us the third order one. And so that's what I'm doing. The third order means I need 3 derivatives. So I computed 3 derivatives. Okay, so now I have to evaluate all these at the value 81. Because that's the center that I'm interested in. Now, you might find this sort of, there's an easy way to think about this, and then there's a pain in the you-know-what way to think about this. Notice that the exponents on all these are to the power 1/4. So 1/4 is, so what you could do is you could kill a lot of this ugliness right away if you recognize that the fourth root of 81 is 3. So let's do this. So what is f of 81? F of 81 is the fourth root of 81, which is 3. Okay. Well, what's f prime of 81? Well, we got to remember what that is. Well, that's 1/4 81 to the negative 3/4. So here's how I would encourage you to think about this. This is the fourth root of 81 raised to the power negative 3. So that's 1/4 times 3 to the negative 3, which is 1/4 times 27, which is, to not make an error, let's use a calculator. And to save time. So what, 108, right? Yeah. By the way, you could have gone to a calculator much sooner, but I'm just, you know, suffering through this fun. And then the next one is you plug, what is the second derivative? The second derivative is negative 3/16. And then it's 81. And then we were, what, negative 7/4. So we can sort of take a shortcut now. This is, was it negative 3/16, right? Yeah. So it's negative 3/16. And then 81, once you take the fourth root, it's just 3 to the negative 7. And so when you compute this, you should get negative 1 over what? Let's see, 23328. Let's just double check that. So So 3 to the 7th times 16. So that's 3 divided by that. So did we get the correct answer? Yes or no? I think that's, oh no, I wrote it backwards. Oh my God. Bear with me. I should be losing my mind. I'm cheating the system. This simplifies to, or not simplifies, but when you do the arithmetic, it's minus 1 over 11664. I was getting ahead of myself. And for the sake of argument, let's briefly do this one. I'm not going to write out all the steps. I think you could do the arithmetic. It's 21 over 64, and then 11. So it's 3 to the 11th times 64. There's a 21 there. So when you compute this creature, you get this. So all I've done, and this just shows you how tedious this can be when you're not centering it at 0. All I've done is computed these coefficients. I haven't done anything else yet. Does anybody have a question? All right. Any comments? Anything? All right. Is anybody awake?
You've proven your point of how tedious it can be when it's not at 0.
I'm just asking. What's happening? Okay. So now we can build this creature. So P sub 3 becomes, it's f of 81 plus f prime of 81 times x minus 81. And then it's plus f double prime of 81 over 2 times x minus 81 squared. And then the last one is the third derivative, evaluated at 81, over 3 factorial, which is 6. And then this is x minus 81 cubed. So what do you end up getting? You get 3 plus. I'm going to write it like this to save space. This is x minus 81 over 108. Yikes. And then it's x minus 81 quantity squared over. Now I have to take this number up here, which is 1 over 1166.4, and I have to divide that guy by 2. So let's see what that is. So 11,664 divided by 2. No, not divided by 2, times 2. So I'm dividing. And so you get 23328. Yeah. Yikes. And by the way, that should be a minus, though. This is a minus sign. So this is a very tedious calculation. And then lastly, you get this 7 business. So this is x minus 81 cubed all over. You see you have the 7, so there's going to be a 7 out front. And then you take 3779136 times 6. And when you do that, you get 226. 74816.
Yikes.
Yeah, you ain't kidding. That's exactly what I was just going to say. Woo. So that is the Taylor polynomial centered at 81. Not a fun calculation. Now, to be fair, software can do this for you now. So you could have easily told a computer to get this for you.
Is this 74816 or 47816?
Say that again.
Like on the denominator,
Oh,
is
did I go backwards? Maybe I did. Let me see. 7, 4. Yeah, I have 2267. Oh, yeah. I said, you're right. I don't know that that's going to matter, but it is an error. So this 4 and 7 should be switched. Is that what you were suggesting?
Yes.
Yes, you are correct. I was wrong. So it should be what? I got to look at my calculator now. 7, 4. Yeah. Yikes.
Big oof.
Okay, so that was the first part of the problem. Does anybody have a comment or a question? That was ugly. Okay, so what we know, though, is we know that we can approximate it. So we know that f of, say, 79, which is the fourth root of 79, is approximately p sub 3 of 79. And so now you can just go plug 79 into that above expression. So what is it? It's if we just, so the first one is 3. And then when you plug 79 in, you get minus 2 over 108. And then you get minus, when you plug in 79, you get 4 over 23328. And then you get plus 7 times, put in 79, you get minus 2 cubed, which is minus 8 over this number, 22674816. Now, of course, at some point you just go to a calculator, so let's do that. So this is tedious as tedious can be. Let's hope I plugged it in right. And when we do this, we get some monstrosity of a fraction. It's 8555051 over 2834352, which is approximately 3.018. Say 3. So that is what we approximated using a Taylor polynomial. All right, so someone has a question. Alyssa, should it be 3 plus -2? Let's go back. So what is the function? So that's a good question. It should be 3 plus. This should be a plus sign right here. So that is a mistake, which needs corrected. Did I make any other errors, though? So barring I didn't make any other errors, which is okay. Let's just double check. Yeah, I think that's correct. All right, now I think I got it correct. So the answer is this is wrong. Let's switch it. The denominator is the same, but the numerator will be slightly different. It's 845,005 or 0075. And of course, when you divide this out, you get 2.98, say 13, which actually makes more sense than the incorrect one we just had. So what do I mean by that? Well, if you went to a calculator and checked this, the fourth root of 79, for instance, Google tells me it's Google gives me 2.9813, so I'm accurate to Google's algorithm to at least 4 decimal points. Does anybody have a question about this? Could imagine that this is challenging. I mean, think about how many errors I just made. Or how many errors I made, I should say. Does anybody want to talk about this? Alyssa, I think you fixed our error, so that's good. We're paying attention. So we know at least 2 people are awake. No, 3. Abdullah, no, Aziz, no. Daryl and Alyssa so far. No, Abdullah, you did too, yes. So 3 of you are awake. The rest, everybody's sleeping.
I have a question.
Yes. Who else is awake? This is good. Yes, what's your question?
Okay, so in the beginning, like when we wrote out, like when we evaluated each different expression at 81,
Yes.
like how much would you like us to write out when we do it for like the
When you say at the beginning, you're talking about this page right here?
Yes.
Oh, I don't care if you just plug it into a calculator. Here's the thing. I mean, you guys got to remember, we're different age levels, right? So when I was learning how to do all this years ago, they didn't have calculators that gave you exact answers, like in fractions. So I'm sure now that the calculators, if you plug these things in, it'll spit out the fraction. Does that make sense?
Yeah.
I don't care how you get 1 over 108. I don't care how you get 1 over this. I don't care if you use a calculator or you do it by hand. That's up to you. Does that make sense?
Yeah.
Yeah. So I think the question you're asking, Jem, is what do I have? All this stuff that's in between, like 81 to the negative 3/4 and then all that. I don't care if you show that work or not. But I do encourage you to learn how to do this. Look, I could go, I mean, here.
Because I wrote it out as well, but I just wasn't sure like how much you would want to see.
Oh, that I wouldn't be picky about that. No, that's fine. If you want to, don't forget, if we're thinking about what a polished scientist or mathematician would do, I mean, if I were writing this for like some other thing, not teaching you, I would leave out the calculations. I mean, I would assume that the reader knows how to calculate, powers. Do you understand what I'm saying? I'm just writing it out here because there's no doubt that when you're trying to learn this, some of you, if I just wrote that it equals 108, some of you'd be like, how the hell did you get that, right? So I'm at least showing you that you could do it by hand if you so desired, but this is much easier to do on using technology, calculator, software. Here, let me show you what I mean. So let me show, look, let me share a screen with you. So hitting the wrong button, hold on. So look how software can do this for you. Now, if I go to Wolfram and I just type, if I type Taylor polynomial for the function, I can just tell that to Wolfram and it's going to spit it out for me, guaranteed. Yep, there it is. And if you look, it gives you it. Now it's actually given us the Taylor series, but we only cared about the first 3. So if I you'll notice that these numbers that we have here are the same ones that I calculated tediously by hand, like a numbskull. Does that make sense?
Yeah, that makes sense.
See, I'm not going to be picky about the calculation details. What I'm more interested in is, what I would be picky about, though, is the actual calculus. Like, do you explain your calculus? I don't care that you explain your arithmetic. I will give you all the benefit of the doubt that you know how to do arithmetic and that you know how to use technology to do and help with arithmetic. What I'm interested in is you understand the calculus portion of it. Okay, does anybody else have a question about this particular problem? It was a challenging one, to be sure. Okay, okay, so that brings me to the next point, which is the new homework. Yeah, what's up?
Never mind, I saw the negative.
We good?
Yeah.
Yeah. All right, so if I go to the most recent homework, which I just posted, does anybody have a particular question about homework 12? Because we did examples of problem 3. Those are tedious and a pain. You just got to suffer through them. We did examples of 4, and we started to do things of 5. And I really wanted to talk about where we left off last class, so I put that on the homework. You'll notice number 7 is the problem we tried to handle last class. So does anybody have a particular question before I talk about 7? Okay, good. So let's talk about that. What you'll notice, by the way, is that these problems here, problems 5, these limits will all work out nicely. We did one like B. So you just have to, A and B are pretty straightforward. C requires a little more ingenuity. 6 it requires something, and we'll look at 6 in a second because that's an extremely important integral. So what I would like to do now is let's talk about 7. So number 7 was started last class. So we tried to compute this limit. Using Taylor series. And what we tried to do is we tried to note that e to the negative x is equal to 1 minus x plus x squared over 2 minus x cubed over 3 factorial plus, and then these signs alternate forever and ever and ever. So what we found is we found a dead end. So we got nowhere. Why? We got nowhere because x cubed times e to the negative x. This guy would then become x cubed minus x to the 4th plus x to the 5th over 2 minus x to the 6th over 3 factorial, etc. there was no, we couldn't figure out a way to take the limit of this. It just didn't work. Every term was going off to infinity. And then I said to you, why? What was bad about this? What was happening that was very much not good? And it's not easy for beginners, or maybe even those who've done well in calculus, to even see what the issue is. But it goes back to something, Jeff, I believe, I keep calling you, yeah, it was you, Jeff. You said a few classes ago, when we weren't even talking about series, Jeff made a point, how accurate are these approximations? And one of the subtleties that he wasn't really trying to hit on, but it allows you to start thinking is, look, that power series that I have written right now, where is that good at? Well, we know it converges everywhere because e to the x converges everywhere. The power series for e to the x converges everywhere. So does this. The problem is that the terms in the beginning are dominating. Look at the exponents, and you have x to the fifth, x to the sixth over these numbers. What's hard to see is that these ratios of each term, x to the something over something factorial, it looks like the exponents are growing faster than the denominators, but they're actually not. Those factorials are going to eventually grow faster. And that's what's going to force the series to converge. The problem is, if we are centering, look what we're trying to do. We're trying to be we're trying to have our cake and eat it too. We're trying to take a limit at infinity, correct? But we're using a series centered at 0. And the problem with that is that both, well, let me put it this way. The problem is that by doing that is we are introducing a competition between x cubed and e to the negative x. And those powers in the power series want to go off to infinity. So what we're doing is we're trying to study a battle. And by the way, if you're still not quite sure the point I'm trying to make, maybe you can take your time machine back to Calc 1, because I could have given you this limit in Calc 1. This limit is going to be 0. And one way to study this in Calc 1 would be to apply L'Hopital's rule. But the method we're trying to do right now is not working. And so we realize that it's not working because we're trying to study something about large values of x by using an approximation that is centered at 0. So what if we tried another way? What if we tried to rewrite the problem so that this issue would disappear? And we're not making it go away. We're not doing magic. We're just trying to take advantage of the good behavior and ignore the bad behavior. So what if we would try to write it like this? What if instead you write x cubed and then you divide it by e to the x? How might we reason this? Well, we might reason that x cubed over e to the x is approximately, let's write this in this insanity, or not approximately, that's not what we want. We know that it's equal. So what if instead we write this? And then we tried to do something that perhaps you maybe remember from an algebra class. Maybe we say, let's try like some sort of polynomial division. Can we divide this? So let me be very specific. So what if I took this and divided? So let's go to the next page and set it up and see if we can see a pattern. So we'll go the old-fashioned way. We want to take x cubed and we want to divide it by this creature. So let's just set this up just like we were doing long division way back in elementary school. So how many times does 1 go into x cubed? Well, we would say x cubed. And then x cubed times 1 is x cubed, and then x cubed times x is x to the 4th, and then plus 1/2 x cubed squared is x to the 5th, and then you keep this pattern. You know, we're fishing for things. And so what was the next step when you did long division as a kid? Then you would subtract. And when you subtract, this goes away, and so you're left with negative x to the 4th minus 1/2 x to the 5th minus blah, blah, blah. And so then you play, okay, what happens now? How many times does this go into this creature? Well, what would be the next thing you plugged in? Well, now you do the next guy. What was the next guy? The next guy was x, so you might reason as follows. Now, by the way, notice I'm using some very, I'm being very careful with my words. I keep saying you might reason. I'm not suggesting that this is going to work. So the next guy would be maybe minus x cubed. Why would I do that? And at this point, you seem like, once again, we're stuck. Are we doing something wrong? Are we just not making the obvious connection? Are we trying to make illegal rules? Are we trying to create illegal mathematics?
I have a question.
Yes.
Why did the second term end up being negative x cubed?
Well, again, I'm asking. I don't know.
Okay.
Right? Do you understand what I'm saying? So
Yeah.
I'm trying to mimic polynomial division to see if it works. And what I'm saying is, how did we do, you know, so maybe this will help. Let me take a different color. I'm trying to brainstorm ideas. I'm trying to discover something. So let's go back to a much simpler, easy example you'd have done maybe in an algebra class. Let's take the following. Let's take x plus 2, and let's divide it into something we know it divides into. How's that sound? We know this is going to divide into x squared plus 5x plus 6. So what would you have done as a student in an algebra class? You would say, okay, this goes in x And then x times x is x squared, and then x times 2 is 2x, right? And then you would subtract, and this terms go away, and you're left with 3x. And then you'd play the game again. How many times does x go into 3x, right? And you'd say 3 times. 3 times x is 3x, and then 3 and 2 is 6. And then when you subtracted, you got a remainder of 0. Now, maybe you guys remember this, maybe you don't. So what I'm trying to do is I'm wondering, is there some sort of analogous argument to this that I can do with series? You understand what I'm saying? Maybe you do, maybe you don't. I don't know. I'm not even pretending that maybe you're going to see the connection at all. I'm just hinting at trying to discover something. Can we discover something? Can we not? Now, there's a couple big differences between what's in red and what's in blue. In red, I was writing things in decreasing. The powers were decreasing. Whereas here, I'm not doing that. Here, I can't write my power series in decreasing in terms of their exponents because it increases forever. But what I'm wondering is if there's some way I can represent this expression. And it's looking like I can't. But then you might counteract yourself because you might say, okay, O'Grady, well, you just did an example before where we just chose the first 3 terms and we got information. So you might say, well, why don't I just take the first 3 terms of this, which I can clearly divide, and see what I get. So let's try that. And again, if you're confused at any point, stop and yell, because I'm not trying to prove a specific point here. I'm not trying to, I'm trying to solve a specific problem, but I'm trying to do it in a way where we might discover something. So, let's think of it this way. So perhaps the issue is that we are concerned with x going to infinity, but e to the x, which is equal to the following, is centered at 0. Maybe that's the big issue here. Maybe the big issue is that we're trying to get information about what's happening way out in infinity, way out that way, but we're using information that's originally good at 0. So that's one thing. So now let's rephrase it. But we should expect x cubed over e to the x to be approximately say x cubed over 1 plus x plus 1/2 x squared out to any desired n we want. And if we think about that for long enough, we should clearly expect the denominator to get very, very large and destroy the numerator. I mean, this ratio, if you think about just plugging in numbers, you would think that it has to go to 0. But the question is, how do you get that? How can you sort of massage the power series to get that? We have a ratio. We expect that it has to be equal to something. Well, what is that something? And can we get it through this division that we're trying to get? So let me come full circle before we get too far out of it. Another way of thinking about this, and this is my last point. We got info about, I think it was sine of 5x over x using series. So we think we should be able to do the same for, say, x cubed over e to the x. And of course, the question is how? So I think it's something that is worth you thinking about. It's something that I think it's worth you trying to get to the bottom of. So, maybe you get some help by going to the internet and asking, what's the power series for? Or going to Desmos and graphing it. Look, one of the things I'd really like to encourage you guys to do is to discover things, not just stress about following procedures, not just stress about memorizing facts or procedures, but to try to discover things, try to create new ideas, have sort of conjectures and figure out how you can maybe verify them logically. Bless you. Was that a cough or a sneeze? What was that?
Sneeze.
Oh my God. You gotta.
Coronavirus.
I hope not. I hope not. All right. Does anybody have a question? So we'll leave for that. By the way, one thing I should have mentioned, because this is important. I'm going to, as I said, I'm going to give you guys a final. But one of the things that I've thrown around is if someone, instead of you taking a final, if you'd prefer to do a project, I have projects that I would be willing to allow you to do in lieu of a final. So I'm going to say more about that later. But one of the, I'd like you guys to transition from just what's the answer to can I discover something, can I create something, can I problem solve in a more general sense, because that's really what mathematics is about. It ain't about these calculus books that are like a damn cookbook. Math is much more exciting than just following procedures. So I don't know, maybe you'll give that question some thought. Maybe you'll see why some of the stuff we did doesn't work. Maybe you'll see what could work. And maybe you'll learn something. Okay. Does anybody have a question before we move on? What time is it? 3 o'clock. It's almost time to go. Woo. I want to do one more example that we've already kind of done before, but I want to point out its importance again. Uh-oh. Is that someone saying something? Or is that just my computer making noise? Let's check. Got the chat button? No chat now. Okay.
Would you do it by parts?
What's that?
Would you do it by parts?
Well, do what? I'm not integrating anything. I mean, you can't do it. You can't do it by parts. Integration by parts only makes sense when you're integrating. I mean, we're not talking about integrating anything right now. We're talking about computing a limit. Okay, let's do one more example that's of importance. And so if you look at the homework, you'll see how I worded this one too. Number 6, I said integrate this using the first 5 terms of a series and ask yourself, I want you to explain, is the approximation good or bad and why? How do you know it's good? How do you know it's bad? So series, let's do this. I don't want to do the same one. It'll steal the fun. So series are also useful for complicated integrals. So let's take the integral from 0 to 1 of something like sine of x over x. Now, this is an integral that you could not evaluate exactly. And the reason for that is we don't know, I shouldn't say we don't know. There is no closed form antiderivative for sine of x over x. The fundamental theorem of calculus doesn't apply. I hope you think about what I mean by that. And that is you could spend the rest of your life trying to find an antiderivative for sine of x over x, and you're not going to find it. At least in a formula. Now, if you went to the internet and tried to ask the internet to integrate this, they're going to tell you this function called the sinc function or something. Some advanced, what we call special function. So anyhow, what we could do is we can say, okay, this is equal to this integral. What's the sign? Sign is x minus 1 over 3 factorial x cubed plus dot, dot, dot. And then this is all over x. And then we could say, let's pick off the first few terms. So let's just say, let's pick off the first 3. So this would be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th all over x. So notice I'm using an approximation now. And then we can divide the x into each piece. And when you do that, this is now not a difficult integral to evaluate because it's a polynomial. What does this become? This becomes, well, let's just write it out. You can fill in the details. When you integrate and plug in, you get 1 minus 1/6 times 2, so that's 1 over 12. And then it's plus, I'm sorry, 3 times 6. This is 18. And then this becomes plus 1 over 120 times 5. That's sloppy. And of course, we can tell you what this is. This is, go to a calculator, if you will. So 1 minus 1/18 plus 1 divided by 1. So as long as we didn't make any errors, this is equal to 1703 over 1800, which is approximately 0.946. Now, if you went to and used your numeric integration or something to integrate sine x over x, or you went and reasoned things, you would see that the answer we got is pretty accurate. Does anybody have a question about this? All right, if you guys don't have any questions, I say we end it here, and you guys got to try to finish these problems. And if you have any questions Thursday, we can finish it up, because then we're going to start some new stuff on Thursday. Comments, questions?
Thank you, Dr. Gray.
Hey, thank you guys. And by the way, do not, again, let me repeat. I know some of you have probably emailed me and some of you haven't gotten responses. That doesn't mean I don't like you and I'm ignoring you. That means they're getting buried. So if you have questions, just keep sending the damn email over and over again. I promise I'll get to it. And if you want to set up a Zoom meeting, I'd be happy to do that. If you have specific problems and maybe you don't have time for Zoom meeting, just tell me what homework and what problem, and I will do. I know Katie already did that, and I will do my best to get that to you. Just keep blowing my email up. I'm trying to get as much help as I can for you guys. All right, I'm going to end recording now.